Hi, everybody. We're taking a look at the section 10.5 on Achieve, and the primary topic in this section is the ratio test. There's also the much less important root test on the occasional problem. But let's go ahead and get started here with the first question. It says, apply the ratio test to determine the convergence or divergence of the series. And then, of course, when the ratio test is equal to 1 in the limit portion, then we know that the ratio test is inconclusive. Okay, so the problem I was given is the series of 4n plus 2 over 3n cubed plus 1. So I needed to determine what the absolute value of the a sub n plus first term over the a sub nth term would be. Remember, a sub n is just the general term of the series in question here. So a sub n plus 1 is just my series general term evaluated when n is equal to n plus 1. That's what I did. I said 4 times n plus 1 plus 2 over 3 times n plus 1 cubed plus 1. And then for the dividing by a sub n, I just multiplied by the reciprocal of a sub n. Now, in most of these problems, and this one included, I just ignored the absolute value because we know our values of n are positive anyway. They go from n equals 1 to infinity. So the absolute value does nothing in this problem. I just dropped it. Now, what I've done from this step to this step is I've collected my like groups. My linear function, this one's going to be 4n plus 6 over 4n plus 2. And then my cubics, I have 3n cubed plus 1. This denominator, I don't want to have to worry with expanding out n plus 1 cubed. I just leave it 3 times the group n plus 1 cubed plus 1. Now, we're supposed to find the limit as n approaches infinity of this expression a sub n plus 1 over a sub n. So it's the limit as n approaches infinity of this simplified form of that expression. Now, when I take the limit as n approaches infinity, I know anytime I have an expression that has a polynomial in the numerator and denominator, all I need to do is look and see if the degree of the numerator and denominator is the same, and if they are, then the limit is going to work out to whatever the leading coefficients are. And that's the same case in both of these two fractions. The first one, the leading coefficients are 4 over 4. The second one, does it matter that this is 3n cubed and this is 3 times n plus 1 cubed? No, it's still a polynomial in which the leading term would be 3n cubed. So the rest of the terms in there doesn't matter. And you just say, well, again, it's going to be the fraction of the leading coefficients, 3 over 3. So clearly, my limiting value is 1. And whenever the limiting value of the a sub n plus 1 over a sub n is equal to 1, your ratio test is inconclusive. So this series could converge, it could diverge. It's just the ratio test is not going to tell us. And so you'll see I had to check the answer of this test is inconclusive. Now, for the next question here, when I look at number 2, well, if I can get to number 2, there we go. It's the series where I have 9 to the n divided by n to the 100th. All right, so you'll see I went in and said, well, the ratio test is going to require me to do the absolute value of a sub n plus 1 over a sub n. Yet again, the absolute value is not needed. So I said, well, a sub n plus 1 is going to be 9 to the n plus 1 divided by n plus 1 to the 100th. Now I'm multiplying that by the reciprocal of a sub n to the 100th over 9 to the n. Now I need to simplify. I put my two terms to the 100th in the first fraction, and then I know 9 to the n plus 1 means 9 times 9 to the n. Now that 9 times 9 to the n can cancel with that 9 to the n in the denominator, and I can say, well, then that's just going to give me 9. That 9 is going to go over and multiply the n to the 100th power. Let's see if I can make that a little more clear here. There, that's a little better. And then my denominator, the 9 to the n canceled, and you'll just have the n plus 1 to the 100 over there. Now, my limiting value here in this problem, in your numerator, you have the 9n to the 100. In your denominator, you just have the n to the 100. Yes, there would be more terms. We could care less about them. because whenever you need to take the limit as n approaches infinity, all you need to know is that the degree of the numerator and denominator is both going to be 100. So the limiting value is going to be the fraction of those leading coefficients, which in this case is 9. Now, every time the ratio test has a limiting value of greater than 1, you know that the series diverges. So the ratio test is telling me that the corresponding series in this problem diverges. And you'll see where I chose that on here, series diverges, and they liked it. We go to the next question. In this one, I have 4 to the n divided by n factorial. As soon as I see this problem, if you have a factorial in that denominator, this problem is going to converge because factorials get large really quickly, even faster than exponential functions that you have in your numerator. So I already know it converges, but they ask us to show that by the ratio test that it converges. So I can say, okay, I can do that. I went in and said the absolute value of a sub n plus 1 over a sub n. A sub n plus 1 is going to be 4 to the n plus 1 power divided by n plus 1 factorial. You multiply that by the reciprocal of a sub n factorial over 4 to the n. Now I know that 4 to the n plus 1 means 4 times 4 to the n. That 4 to the n is going to cancel with a factor of 4 to the n in the denominator. Now, as far as the factorials, I have the n factorial up top, but n plus 1 factorial means n plus 1 times n factorial. So I have the 4 to the n's cancel, the n factorials cancel. I'll be left with a 4 in the numerator and an n plus 1 in the denominator. Now, we're taking the limit as n approaches infinity of this expression, which simplified down to this. Clearly, if n goes to infinity, 4 over n plus 1, that fraction goes to 0. Anytime the ratio test has a limiting value less than 1, you know that the corresponding series converges absolutely. That's the whole definition of the ratio test. And so you can say, well, all right, then this series does converge absolutely. And you can say, well, that is absolutely the correct answer choice here. For the next one, we have n factorial over n to the 6th power. Now, for the same reason that just by looking at it, I knew that the last one converged because that factorial gets large really quickly. I know this one will diverge because that numerator is getting large quickly, much more quickly than that denominator. Even if that denominator was n to the 6 trillionth power, this problem is going to diverge because n factorial is going to get larger as n approaches infinity. Now, in order to see that in action in this problem and how the ratio test can show you that, we do our absolute value of a sub n plus 1 over a sub n. That gives me n plus 1 factorial over n plus 1 to the 6th, multiply by the reciprocal of a sub n to the 6th over n factorial. Now I can see that my n plus 1 factorial is n plus 1 times n factorial. That n factorial will cancel with the n factorial in the denominator. My n to the 6th, I'll go ahead and group that with my n plus 1 to the 6th in the second fraction. Now, notice what this is going to give us. We're going to have an n to the 6th times the group n plus 1 in the numerator. And I'll just have the n plus 1 to the 6th in the denominator. Now, what I've done here is I went ahead and distributed this n to the 6th through that group, and I can say, well, then clearly my numerator is going to be a polynomial in terms of n with a leading term of n to the 7th. The rest of the terms are really irrelevant. The denominator would be an n to the 6th, and again, the rest of the terms are irrelevant. Because now that you can see, well, if n goes to infinity, this numerator is going to be infinitely times larger than that denominator because it's another power of n greater. So anytime that limiting value goes off towards infinity, or as we know, anytime it goes off to a value greater than 1, the corresponding series is going to diverge. Well, this is extremely conclusive evidence that n factorial over n to the 6th diverges. And you can see now that the diverges is the answer I chose for number 4. For number 5, similar type of question. And again, these Yes, I want to show out the work because I want us to get experience using the ratio test, but there is no reason that you couldn't have just looked at this original problem and said, I know it converges. How do I know it converges? Because your numerator is a wimpy little polynomial function n to the fifth. That denominator is a factorial. As n gets large, factorials grow enormously quickly, way more quickly than geometric or way more quickly than exponential functions, and way more quickly than a little polynomial function. So even if that would be n to the 5 trillionth power, this still is going to converge. The ratio test makes that all very, very clear by just going in and saying, well, let's figure out what the a sub n plus first term is. You'd have n plus 1 to the fifth for the numerator. Your denominator, you'd have 2 times n plus 1, so that's going to give you 2n plus 2, and plus another one. That gives me 2n plus 3 factorial. Now, we're multiplying that by the reciprocal of a sub n, which is 2n plus 1 factorial over n to the fifth. So I grouped my two terms to the fifth power together, n plus 1 to the fifth over n to the fifth. Now let's multiply that by our factorials. I left my 2n plus 1 factorial alone in the numerator. And then please remember what 2n plus 3 factorial means in the denominator. It's 2n plus 3 times every integer value less than it all the way down to 1. So I can say, well, it's 2n plus 3 times 2n plus 1 times 2n plus, times 2n plus 2 times 2n plus 1 factorial. The 2n plus 1 factorial portion would cancel, but it's not going to cancel out these two terms. So then I come down here and say, well, the ratio test is going to tell me that the limit as n approaches infinity of this expression, I'll have my functions to the fifth power times 1 over these two terms, the 2n plus 3 times 2n plus 2. And then I can say, if I multiply that out, I can see that that denominator is going to be a polynomial with a leading term of 4n to the seventh. The numerator is just a polynomial with a leading term of n to the fifth. If I allow n go to infinity, your denominator is 2 factors of infinity greater than the numerator. This is going to simplify down to be 1 over infinity, which goes off towards 0. You can say, well, okay, anytime the ratio test is converging down to a value where it's less than 1, then you know that the series is going to be convergent absolutely. And that's what it says here. The ratio test determines the series converges absolutely. And you'll see I chose here the series converges absolutely on that one. Now, for the next question here, number 6, here's the work I did for that. I have the series 4 to the n divided by n to the k. I could see a student getting confused on this one. Let's talk about the work that I've done on this one. I said, well, I'm going to go in and use the ratio test to try to figure it out. A sub n plus 1. Now remember, k is what you're solving for in the end. It's not the term that's changing from one term to the next. That's the n. So a sub n plus 1 is going to be 4 to the n plus 1 divided by n plus 1 to the k. Then we'll multiply that by the reciprocal of a sub n, which is going to be n to the k over 4 to the n. Now when I simplify that, I know 4 to the n plus 1 means 4 times 4 to the n. So when you divide that by 4 to the n, you'll just get a 4 in the numerator. That'll be multiplied by n to the k. My denominator, the exponential function canceled out, but I'll still have the polynomial n plus 1 to the k power down there. So now, in order for the ratio test to work, I would have to be able to take the limit of this and show that the limit is less than 1. And I'm supposed to find the value of k that can make this happen. Well, there is no value of k. Well, think about why. Here's your problem. You have 4n to the k in the numerator. Your denominator is n plus 1 to the k. No matter what power k is, your numerator is going to be a polynomial degree k, and it has a coefficient of 4. Your denominator is going to be a polynomial degree k. You'll have other terms that are infinitely less than the size of that. We don't care about those. It's only the leading term that would matter. So no matter what the value of k is, your limiting value is always going to be 4 here. And what do I know about that? I know since the limiting value is 4, that could never ever be less than 1. Thus, this series is always going to diverge regardless of your choice for k. Now, in this problem, they told us if no value of k existed that could make this converge, we simply say k equals does not exist, DNE, and that's what I did there. When we go on to the next question here, these next two here, number 7 and number 8, are kind of cool, but I can see that they could also be confusing. So let me talk about what they're doing here. They're asking us to assume that the absolute value of a sub n plus 1 over a sub n converges to 1/5. Please think about what that means. It's telling you that the ratio from one term to the next is a ratio of 1/5. So every successive term in our series is 1/5 the size of the previous term to it. Okay, so that's essentially telling you it's an R value of 1/5. Well, all right, then that a sub n, if that's the general, if that's the how that limit simplifies down, and it's telling me that each term is 1/5 the size of the one before it. Well, think what happens if you put that a sub n inside of a summation multiplied by 4 to the n. Well, I'm thinking a sub n is the same thing as 1/5 to the n, since every term is 1/5 of the size of the term in front of it. Well, 4 to the n times 1/5 to the n, that would give me 4/5 to the n. What do I know about 4/5 to the n? I know it's a geometric series in which each term is going to get smaller by a factor of 4/5. Does that converge? Absolutely it converges. It converges absolutely. And that's because the R value is 4/5, and you know that 4/5 is less than 1. Geometric series always converge as long as you're multiplying by a term that's going to make each successive term smaller. And in this case, if you're multiplying here by 4, but your general term is getting smaller by a factor of 1/5, then every term is getting smaller by a factor of 4/5, which will make it converge absolutely. For number 8, extremely similar question here. It's saying, well, what if your a sub n plus 1 over a sub n converges to 1/7? What can you say about the convergence of the given series a sub n quantity squared inside the summation? You can say, well, if a sub n plus 1 over a sub n is equal to 1/7, then naturally a sub n itself is going to get smaller and smaller and smaller by a factor of 1/7 as it goes from the nth term to the n plus first term. But now if I'm squaring that factor of 1/7, 1/7 squared would be 1/49. So I can say, well, that means each term of the series is going to get smaller by a factor of 1/49. And I can say, well, then it's definitely going to converge, and it will converge really quickly. These terms are going to get tiny very fast. So I can say, since the R value would be 1/49, which is less than 1, this is really just what I've done in problem 7 and 8 is the geometric series test. Since the R value is less than 1, we know it converges absolutely. Now, don't get confused about that converges conditionally and converges absolutely. It's always going to be converges absolutely unless you have some factor of an alternating series where you have -1 times something. And if the only way it converges is because of the alternating sign, that's the only time we say converges conditionally. There's no negative signs or anything in these, so all of these are converges absolutely. You don't have to depend upon the sign changing from positive to negative to ensure that that converges. That's why we're saying converges absolutely. For the next problem here, number 9. Oh, and this one's really quick. We have 1/4 to the n. Since I did geometric series tests for the last two, I kind of kept that on this one. Now, technically, the problem says root test, but root test is silly here. You just say 1/4 to the n. That's the same thing as 1/4 to the n. What do I know about 1/4 to the n? It's a geometric series with an R value of 1/4. Since the R value is 1/4, which is less than 1, we know this series converges absolutely. And again, it definitely converges absolutely. The only time we would say it just converges or converges conditionally is if the convergence is dependent upon an alternating sign. This sign is always positive, converges absolutely. The next one I did use the root test on. So number 9, it asked us to use the root test. I chose not to because it was silly to use the root test on such an easy problem. 10, it's not too much harder, but I did go ahead and use the root test on it. What the root test asks us to do is to take the kth root of the a sub kth term, or the nth root of the a sub nth term. They're using k here. So I took the kth root of this general term. When I did that, the kth root and the kth power cancel. So I'm left with a fraction on the inside. Now, what does the root test say? Well, once you take the kth root of that group, then you're supposed to take the limit as k approaches infinity of the remaining expression. And if that expression is less than 1, that's evidence that your series is going to converge absolutely. Well, this one's clearly less than 1. It's going to be 1/6. So I can say, since the limit of my root test is 1/6, which is less than 1, this series is going to converge absolutely. And that's by our root theorem test. And you can see I marked the converges absolutely there. For number 11 here, we have n to the 8th over n factorial, and it's asking us to use any type of convergence or divergence theorem. This one, again, I can just look at it and say it converges. Why does it converge? Because the numerator is a wimpy polynomial. The denominator is an enormous factorial. Factorials grow so much more quickly than polynomial functions do. So I can say, I know that this function will converge since the denominator grows much, much more quickly than the numerator. I went ahead and chose to show that with the ratio test, since that's the main test of this section. So I said a sub n plus 1, n plus 1 to the 8th over n plus 1 factorial, times the reciprocal of a sub n factorial over n to the 8th. This simplifies to n plus 1 to the 8th over n to the 8th, times n factorial over n plus 1 times n factorial. You can see I canceled out the n factorials. I'll be left with n plus 1 to the 8th over n to the 8th times n plus 1. Now, what I've done in this case is I went ahead and canceled out one of the n plus 1s in the numerator with a factor of n plus 1 in the denominator, and I said, well, then my numerator is going to simplify to be n plus 1 to the 7th. My denominator is n to the 8th, but the limiting value of my ratio test is going to be the limit as n approaches infinity of that expression, which I can see is going to be a polynomial degree 7 in the numerator and a polynomial degree 8 in the denominator. This is conclusive evidence that your denominator is infinitely times greater than the size of your numerator. This fraction is going to reduce down to a 0. And so anytime your ratio test is an answer less than 1, you're supposed to remember, well, then that's conclusive evidence that this converges absolutely by the ratio test. A couple more questions here. Number 12. Notice it gave me the function here, or sorry, the series here, 11 to the 1 over n power. I've answered this one really quickly by just saying all I have to do on this one is the test for divergence. If you remember back to section 10.2, what the test for divergence asks us to do is to take the limit as n approaches infinity of the general term of the series. If you can show that that doesn't go to 0, then the series must diverge. Now, some people try to go too much with the divergence test and they want to say, well, if it is 0, it shows that it converges. That's not true. But it does tell us that if it's not 0, then clear cut, the series does diverge. And that's the case here. If I allow n to go to infinity, this becomes 11 to the 1 over infinity, which is 11 to the 0. We know any number to the 0 power is 1. So you can say, well, the limiting value of the general term is 1. Since that limiting value is not 0, that's conclusive evidence that this series diverges. And then if I look at the next question here, number 13, you can see, again, I put that this one diverged. Why does it diverge? It gave me the series 1 over 2n plus the root of n. Now, what I chose to do with that is, and there's tons of things you could have done with this one, I chose the comparison test. The reason I chose the comparison test is I thought of this right here. So I know that 1 over 2n plus the root of n. Keep in mind, as n is getting large, we know that the root of n is always going to be less than n. So, and I was thinking of, well, this denominator is always smaller than a denominator of 2n plus n, because n is going to be adding more than the root of n. Well, 2n plus n would be 3n. I know conclusively this denominator is larger than this denominator. Well, if you have the same numerator divided by a larger denominator, we know that this fraction is less than that fraction. So I can say, all right, then the general term of the series I'm dealing with is greater than or equal to the general term of this series. Well, what do I know about the general term of this series? I know it's a p series with p equals 1 because the degree difference in the numerator and denominator is 1. So I can say, since 1 over 3n is a p series that diverges since p is 1, please remember the p series test tells you that it diverges anytime that degree difference is 1 or less than 1. Since p is 1, which is less than or equal to 1, this is a divergent series. Now, what do you know? Well, you know that the series in question is larger than this series that diverges. Then by the comparison test, then we can say the series 1 over 2n plus the root of n must also diverge. Since it has a smaller denominator, it's a larger fraction. Larger fractions in there has to diverge inside that series. Fun stuff here. So now, sadly, we've reached the last question in this section, and you might be thinking, well, hey, we want to do more questions. Yeah, I did too. I can't believe there's not that many here. We have the series n squared plus 2n over 4n to the 4th plus 8. All right, guys, so as soon as I saw this, I thought, hey, degree difference in the numerator and denominator is 2. What do I know about that? Anytime the degree difference is 2, it's going to be a p series, p equals 2. It should converge. In order to show that formally, I use the limit comparison test with a p series, p equals 2, 1 over n squared. Now, with a limit comparison test, I don't have to go in and show that one is greater than the other or anything like that. That'd be a little hard-pressed to guarantee that this is greater than that. So instead, what the limit comparison test does is it has us take the limit as n approaches infinity of the general term of the series we need to know something about, usually called a sub n, divided by the general term of the series we do know something about, b sub n, the 1 over n squared. And again, I know that the series 1 over n squared is a convergent p series of p equals 2. All right, what happens when I simplify this expression? Well, when I divide by 1 over n squared, I'd just be multiplying by n squared in that numerator, gives me n to the 4th plus 2n cubed, over 4n to the 4th plus 8, all inside of my limit going to infinity. Since I have an infinite limit, you say, well, the numerator is a polynomial, denominator is a polynomial, the degree of the numerator and denominator is the same. The answer is going to go to the fraction of the leading coefficients, 1/4. So what is this telling us? It's telling us that for large values of n, this series is approximately 1/4 the size of this series. So it's some constant multiple of that series. What do I know about this series? Well, it's convergent. 1/4 times a convergent answer will also converge. That's why we're saying, therefore, the series of interest also converges, because that value is equal to 1/4. Please remember, you would get that same answer anytime the limiting value for the limit comparison test is any number greater than 0 but less than infinity. It has to be some finite multiple of b sub n, and in this case it is. So we would say, since b sub n converges, our series also converges. And why did I choose converges absolutely? Because again, please remember, there are no negative values in here. Could you take the absolute value of that? Of course. You can never, ever, ever possibly get a negative value. The only time you're ever going to choose that converges conditionally answer is in an alternating series where your terms are going negative, positive, negative, positive, negative, positive. And the only reason it converges is because of that alternating sign. So in these problems where there's no alternating sign, you will never choose the converges conditionally answer. This one's converges absolutely because every term's automatically guaranteed to be positive anyway. And once you answer that, you can see, hey, finish that section. So we have one more section to go with the 10.6. We'll be using the ratio test a lot in it too with the power series. It's a pretty fun section, so stay tuned for it.